The Boeing Insitu RQ-21 Blackjack represents a key step in tactical battlefield surveillance. Designed to meet the U.S. Navy's need for a small tactical unmanned air system, it builds upon the earlier ScanEagle platform but introduces enhanced payload capacity, improved sensors, and adaptability for both land and sea operations. Its twin-boom configuration and lightweight structure allow it to be launched without traditional runways, using pneumatic systems and recovered via skyhook technology. This capability gives it a major operational advantage in expeditionary environments. In addition, its ability to operate in high temperature and harsh conditions makes it highly reliable in diverse combat zones where traditional systems often struggle. The integration of advanced camera systems and real-time data transmission further enhances its role in intelligence gathering and situational awareness. Its development timeline, from selection in 2010 to operational deployment shortly after, demonstrates how rapidly UAVs can transition from prototype to frontline use when aligned with urgent military requirements. Moving into more advanced combat concepts, the Boeing X-45 showcases the early vision of autonomous unmanned combat air vehicles. Developed under DARPA's JUCAS program, the X-45 eliminated the need for onboard pilots entirely, allowing ground operators to focus on mission-level decisions and overall strategy. Its stealth-influenced design, blended wing body, and absence of vertical control surfaces emphasize survivability, efficiency, and reduced radar visibility, making it harder for enemy defense systems to detect and track the aircraft during missions. The integration of autonomous flight control systems enabled the X-45 to respond faster than human pilots in rapidly changing combat scenarios, enhancing mission reliability and precision. One of its most groundbreaking demonstrations was autonomous collaboration, where multiple X-45 units coordinated attacks, assessed targets, and executed missions with minimal human intervention. This capability marked a turning point toward AI-assisted warfare, illustrating how unmanned systems could independently manage complex combat operations while reducing risk to human personnel. In contrast to combat-focused UAVs, the Boeing X-51 Waverider pushed the boundaries of speed and propulsion. Designed for hypersonic flight, it demonstrated the feasibility of scramjet-powered vehicles capable of reaching speeds above Mach 5. The Waverider utilized shockwave compression lift, effectively riding its own shockwaves to maintain stability at extreme velocities. This advanced propulsion system allowed the aircraft to operate efficiently at speeds where traditional jet engines would fail, marking a significant leap in aerospace engineering. Its air launch method from a B-52 bomber also enabled it to reach the required altitude and speed before activating its scramjet engine. Its successful long-duration hypersonic flight in 2013 represented a major breakthrough, laying the groundwork for future high-speed strike weapons and next-generation missile systems. Rather than serving as a conventional UAV, the X-51 functioned as a technological bridge into hypersonic warfare. Earlier experimental platforms like the Boeing Condor focused on endurance and altitude rather than speed or stealth. With an enormous wingspan exceeding 200 feet and constructed primarily from carbon fiber composites, the Condor was designed to remain airborne for extended durations. It achieved remarkable milestones, including automated flight from takeoff to landing, and record-breaking altitude performance for piston-powered aircraft. Its ability to stay in the air for over 50 hours highlighted its exceptional endurance capabilities, which were far ahead of its time. Additionally, the use of satellite communication systems allowed full mission control from the ground, demonstrating early advancements in long-range UAV operations. Despite its technological achievements, its limited survivability in contested environments prevented it from transitioning into operational military use. However, its innovations in endurance and automation heavily influenced later UAV designs. Building on lessons from the Boeing Phantom Eye, the Boeing Phantom Eye introduced a pioneering approach to long-endurance surveillance by utilizing liquid hydrogen fuel. This innovation allowed for significantly longer flight durations with minimal environmental impact, as the primary byproduct of its propulsion was water. Designed for high-altitude, long-endurance missions, Phantom Eye aimed to provide persistent intelligence coverage over vast areas, including regions where traditional manned aircraft could face operational limitations. Its advanced propulsion system, supported by turbocharged engines, enabled efficient operation in oxygen-thin environments at extreme altitudes, while its large wingspan and lightweight carbon fiber structure further enhanced fuel efficiency and endurance. Additionally, its autonomous flight systems allowed for precise navigation and data collection over extended periods without constant human input. The UAV's ability to remain airborne for days at a time highlighted the growing importance of continuous surveillance in modern military operations. Although Phantom Eye remained a demonstrator, it illustrated the potential for UAVs to complement or even replace satellites in certain roles, particularly for communications relay, persistent monitoring, and strategic intelligence gathering. On a smaller and more operational scale, the Boeing Insitu MQ-27 ScanEagle became one of the most widely deployed UAVs for real-world missions. Originally derived from a commercial system used for tracking fish, it evolved into a highly effective reconnaissance tool. Its long endurance, compact size, and ability to operate without runways made it ideal for deployment in conflict zones such as Iraq. The use of pneumatic launch systems and skyhook recovery technology further enhanced its flexibility, allowing operations from ships, remote outposts, and locations with limited infrastructure. Equipped with real-time imaging and data link capabilities, it provided critical intelligence support, enabling commanders to make faster and more informed tactical decisions. Continuous upgrades, including night vision capabilities, advanced radar systems, and improved sensor packages, have kept it relevant for both military and commercial applications. The ScanEagle demonstrates how adaptable UAV platforms can transition across industries while maintaining operational effectiveness, highlighting the importance of modularity and technological evolution in modern unmanned systems. A significant shift in UAV roles is seen in the Boeing MQ-25 Stingray, which redefines unmanned systems as force multipliers rather than standalone platforms. Developed from the UCLASS program, the MQ-25 focuses on aerial refueling, extending the operational range of manned fighter jets. This role highlights a strategic evolution in UAV usage, supporting crewed aircraft rather than replacing them. By providing in-air refueling, it enables fighter aircraft to remain in combat zones for longer durations without returning to base, significantly improving mission efficiency and operational tempo. Its integration with carrier operations also reduces the workload on traditional tanker aircraft and enhances overall fleet capability. Equipped with advanced sensors and secure communication links, the MQ-25 can operate seamlessly alongside manned aircraft, providing support while minimizing risk to pilots. By operating from aircraft carriers, the MQ-25 strengthens naval aviation flexibility and demonstrates how unmanned systems can complement human crews in complex operational environments. The most advanced representation of modern UAV concepts is the Boeing MQ-28 Ghostbat. Designed as a loyal wingman, it operates alongside crewed aircraft, sharing data, performing reconnaissance, and even engaging targets when authorized. Built in Australia, it represents a new generation of AI-enabled combat drones capable of autonomous decision-making and coordinated operations. Its modular design allows for rapid reconfiguration depending on mission requirements, and its integration with platforms like the E-7 Wedgetail and F-35 demonstrates the future of networked warfare. The Ghostbat's successful missile engagement tests mark a major milestone, showing that unmanned systems can actively participate in air-to-air combat scenarios. Taken together, these UAVs illustrate a clear trajectory in unmanned aviation. Early systems emphasized endurance and basic reconnaissance, while later platforms introduced stealth, autonomy, and combat capability. Today's UAVs are no longer major tools. They are integral components of a larger, interconnected combat ecosystem. From the tactical flexibility of the RQ-21 to the autonomous coordination of the X-45, the hypersonic innovation of the X-51, and the collaborative intelligence of the MQ-28, UAV technology continues to redefine what is possible in the skies. Outro. Unmanned aerial vehicles, UAVs, are no longer just future technology. They are a present reality shaping modern warfare, surveillance, and aerospace innovation. With rapid advancements in autonomy and artificial intelligence, the line between human-controlled and machine-driven aviation continues to blur. Today's UAVs are capable of complex reconnaissance, precision strikes, and support missions, often operating in environments too dangerous or remote for humans. The next generation of UAVs will not merely assist pilots. They could one day plan, coordinate, and execute entire missions independently, transforming strategic decision-making and reshaping the balance of power in the skies. As these systems evolve, they promise to redefine not only military operations, but also commercial and scientific applications, demonstrating the limitless potential of intelligent, unmanned flight.